have Dr. Ari Friedlaender with us. He is an ecology professor in the Ocean Sciences Department at UC Santa Cruz. And tonight he will share amazing and important research that he, along with collaborators, are conducting with baleen whales in localities in the Antarctic to Alaska. In addition to the research that he does and teaching, Dr. Friedlaender is also very willing and interested in outreach programs such as this to encourage future ocean scientists like you here, and to educate communities about our ocean. When I first asked, when I happened to be at a talk that he gave, and I went up to him right after the program, and I asked him if he'd be willing to speak to us, he said yes within a second. I was so amazed by that. Dr. Friedlaender earned his BA in biology and with an anthropology minor from Bates College in Lewiston, Maine. He earned his Master's of Science in Marine Biology from the University of North Carolina at Wilmington, and his PhD from Nicholas School of the Environment at Duke University in the Duke University Marine Lab. So please give a warm welcome to Dr. Ari Friedlaender.
It's awesome to come out on a Friday evening and see a packed house. And one of the things that's most exciting for me is that this is obviously a community that is not coastal. And one of the things that I really am excited about is sharing the things that we do on the coast with folks that don't typically have an opportunity to either see the coast on a daily basis or may just not be familiar with it, as familiar with it as I am. But as you mentioned in the introduction, I think one of the most important things when we think about conservation of our natural resources is not just having the people that are the most proximate and close to an issue be educated about it, but have it be a much more broad thing. And a lot of the change that we see in policy and in management comes from the ground level up. And so that includes communities like this that hopefully we can encourage to get excited about marine science, come to the coast, visit anytime. I will absolutely say anybody that wants to come and visit our labs, you're more than welcome to, and I'd be happy to show you guys around, and hopefully this kind of stuff inspires somebody to maybe think about wandering a little farther west and learn a little bit more about the oceans. So what I wanted to talk tonight about, and if I start to drown off or lose my pitch level, just someone shout and I'll try and talk a little bit louder. What I want to do tonight is talk about some projects and some data that we've been collecting over the last 10 or 15 years to start understanding how healthy whales really reflect healthy ocean ecosystems, and some basic things that we're doing that have taken a long time to do that help us understand this relationship. Oh, that was it. Okay. So just to start off, I wanted to just show this because the work that we do on whales logistically is an absolute nightmare. It takes a huge amount of energy, a huge number of resources, especially if we're working in a place like the Antarctic. So in order to do that work, we require a lot of collaborators, a lot of time, a lot of energy, and a lot of students. And so the work that we do not only gets funded by government agencies like the National Science Foundation, but I feel really strongly that if the work we want to do is going to have conservation purpose, that we partner with those organizations that can help us take our science sort of to the next level and share it more broadly and make it more digestible to audiences outside of the scientific community. So working with partners like the World Wildlife Fund, National Geographic, and BBC, those are the reasons that we try and partner with those organizations who have similar mindsets. So in terms of my academic sort of philosophy, I did my master's research in an anatomy and functional morphology lab. And basically what that meant was that I learned how marine mammals were put together from the inside out, how they evolved from land animals, how the adaptations that they have for being an air-breathing animal in the ocean have manifested to their body parts. And that understanding of anatomy and then physiology, how you hold your breath and do things in a watery environment, I think really helps you understand or puts you in a good position to understand the behavior of those animals and to study the behavior given the context of how they're adapted. And obviously then that behavior has to be contextualized or related to the environment that those animals are in. And to me, that's what ecology is understanding how the behavior of animals relates to that environment. So I think all of these disciplines that we've been trained in or that we think about all overlap very nicely. In order to do this in a marine system relative to a terrestrial system, we require a lot of tools. So the stuff I'm going to talk to you tonight about, we'll talk about technologies in terms of something called an echo sounder, something that sends a very high frequency signal into the water. It bounces off of things that have a different density than water, and it tells us about how much stuff is in the water column. Then we use things like tags, biologging tags that I'll talk about a little bit more, that allow us to sort of see below the surface, understand how animals are behaving and moving when we can't see them. The output of this is obviously information, knowledge, science, and that's wonderful. It's fantastic and it's great and it makes for good educational talks, makes for great scientific papers, hopefully, but more so I think it helps lend value to conservation. And what I want to sort of speak about tonight is how I think whales represent a really good model for not only, excuse me, I just have a cough from 2 little kids at home, but I'm totally fine. It might sound like I'm going to fall over, but I'm actually okay. But I really think that whales represent a fantastic opportunity to think about all these scientific disciplines and then sort of the, excuse me, the output of this being conservation. Now, why study whales? There's a few reasons that I think they're a really useful thing for us to study. They're a great model for testing fundamental biological, ecological, and physiological principles. The biggest animals on the planet, the biggest animal that's ever existed is a blue whale, and it's around today. So we can learn a lot of things about feeding or being gigantic or the limits of what nature can produce in terms of being an organism that help us understand our natural world. One of the things I want to sort of get through tonight is that I think the presence of whales really reflects emergent properties of healthy ocean ecosystems. And what I mean by that is, think about a whale, and I'm going to talk about how much a whale needs to eat in a given day. And in order for an ocean ecosystem to support 1 whale, 50 whales, 100 whales, there's all these things that have to happen from upwelling, nutrients, sunlight. Everything has to work in concert to be able to support a whale. So when we think about Monterey Bay as being this great haven for whales, it means that things have to be happening there in a very particular way in order for those animals to be there. Then on the flip side of that, we can use whales as sentinels for environmental change. If all of a sudden a place that had whales that was really productive all of a sudden doesn't have whales, that can be an early warning sign that things are changing in the oceans, conditions are changing, it can't support those big things that need a lot of food in the ocean, and we can use that as sort of an early warning sign to study the impacts of climate change. And then lastly, we care about whales for their heuristic value. They have huge societal value. There's a massive industry for whale watching and for using them sort of as a basis for, excuse me, for tourism. Also, what I'm going to talk to you tonight about is that they have ecological value, and their presence doesn't just do us good, but it does ocean ecosystems good as well. All right, here's a little piece of trivia. How many people know when the Endangered Species Act was passed?
1970. With Nix.
73. 73 was the Endangered Species Act. All right. There's another act in Congress, a federal law that's called the Marine Mammal Protection Act, which was basically created saying that any marine mammal that is alive is protected federally from harassment, harm, take whatever we want to do to it. When was that bill passed? Okay, thank you with the mask on. Before the Endangered Species Act. So whales, marine mammals, seals, all of the animals that we think about being whales, dolphins, and porpoises had federal protection just because they're marine mammals, even before the Endangered Species Act. And one of the other main sort of challenges or differences between those two acts, marine mammals were federally protected regardless of whether or not their populations were high or low. It's a proactive piece of legislation. The Endangered Species Act, you only benefit from that when you've been kicked in the butt and you are at the level of a population that really needs protection. So right there, marine mammals have this huge value that we've already applied to them here in this country. Good history. Thank you guys for that. I appreciate it. So going even farther back in evolutionary history, if you want to be big in the ocean, there's been this independent evolution over the last 100 million years, several times, for a feeding strategy that takes advantage of very small things in the ocean. All right? If you think about your food pyramid and trophic levels, at the very base you have all of your producers. Then the next trophic level up are those consumers, phytoplankton, zooplankton, then smaller fish. The farther up you go in that trophic pyramid, the less biomass there is. Okay? So if you want to get big in the ocean, you want to feed on the thing that's the most abundant. The most abundant things in the ocean are the very small fish, zooplankton and phytoplankton. So things like manta rays, basking sharks, whale sharks, megamouth sharks, and baleen whales have all independently evolved a filter feeding strategy where they basically have a huge mouth and they bring in a lot of water and filter out a lot of very small things. We've done some work recently and shown that if you feed on single prey items like a fish or a crab, your body size in the ocean is basically limited to about 30 or 35 feet, which is precisely the size of a killer whale, because there's just not a lot of biomass for you to feed on. So the upper limit for a toothed whale or something that feeds on individual items in the ocean is about 30 or 35 feet. Blue whales get up to be about 100 feet. Basically every baleen whale species is bigger than a killer whale. So there's some really good support for, if you want to be big, feed on little things and figure out a mechanism to feed on a lot of them at a time. Now, baleen whales evolved from land animals that came back into the ocean and turned into air-breathing cetaceans, whales, dolphins, and porpoises. That happened about 50 million years ago. When those land animals went back into the sea, they had teeth, they fed on single prey items because, excuse me, that's what was abundant then. This graph shows us going from 40 million years ago on the bottom to about today, what the size of baleen whales is in the fossil record. And so going from left to right is size. So at the very first mysticetes that you see, or first baleen, those whales evolved about 30 or 35 million years ago, and they were relatively small. They're about 5-6 meters long, 18 or 20 feet long. Huge for a land animal, for a baleen whale, not so big. That coincided, the evolution of baleen, with something called the Antarctic circumpolar current. So about this time in evolutionary history, or geological history, Antarctica found its way to the bottom of the planet, and this current was set up in the ocean that is a persistent current around the Antarctic continent that promotes upwelling of very nutrient-rich water, and you combine that with sunlight in the summertime, and you have massive productivity of phytoplankton and then zooplankton. So there is now a huge prey base that could be fed on. Baleen evolved as the mechanism to feed on that. And baleen is effectively a keratinized structure, just like your fingernails, that hangs down from the inside of the mouth of a whale. There's usually 200 or 300 of these plates. They look kind of like combs, and they sort of form a mat on the inside of the whale's mouth. Take a huge gulp of water, push the water out through this baleen plates. All the small fish and phytoplankton stay on the inside of that, and they feed on it that way. So baleen evolved once the ocean structure had set up for persistent productivity in the Southern Ocean. And then, in the last 4 or 5 million years, things like glacial cycling, upwelling, coastal upwelling like we get in Monterey Bay, became more persistent features of the ocean, meaning there was more and more food to support whales. That allowed their body size to get as big as they are today. So we're really lucky today to be living in an age where the biggest whales that have ever existed are extant. And we can go visit them. And we have blue whales in Monterey Bay just down the coast, which is pretty awesome. Okay, everybody know who this is? Okay, greatest human being maybe on the planet. If we were smart and wanted to do behavior and study animal behavior, you'd get a $2 pencil and pad of paper, find your way into the forest in Gombe, and you'd study chimps like Jane Goodall does, where you can literally witness everything that the animals do, look at their interactions, look at how they do certain things, write it down. But where's the creativity there, right? How are you going to get that wrong, right? You might interpret something wrong, but you're constantly seeing those animals. It's a really smart thing to do. Unfortunately, there are those of us that have decided studying an animal that lives 95% of its life underwater is a good thing to try and do. Obviously, we've made some poor life choices, but it gives us access to have to use a lot of fun tools. And what this image just shows you are some of these big tools that we have to use in order to study sometimes just the very basic things about whales. So using satellite telemetry to tell us about where animals are on the planet. Using drones, like we've got this image here, that literally just tell us how big a whale is. Aerial surveys, acoustic surveys, just to find where these animals are located. Tags that I'm going to be talking about that tell us about how animals are moving underwater. So on and so forth. So we use a huge suite of tools. It's a very multidisciplinary tool set that we need to use, which means we necessarily have to collaborate and learn the ability to communicate across disciplines if we want to study these animals. So what I want to talk to you guys tonight about is how we have asked and answered the very simple question of how much does a whale eat in a day? And in order to do that, the three sort of tools that we're using, biologging tags that tell us about the underwater movement of these animals, how frequently they open their mouth and eat. That is important because then we need drones that tell us about how big the animal is, how big its mouth is, tells us how much water it can actually process. And then if we, use the imaging tools like echo sounders that tell us about how much prey is in the water column, we can multiply the amount of food by the number of times the animals eat, times the number of water gallons that they process. That should tell us something about how much these animals are actually eating. Again, very basic question, very difficult in practice to be able to address. So in order to do this, a bunch of us got together over the last 10 years and aggregated a lot of data. We sort of worked around the planet. You can see where the tag deployments have occurred. We used over 300 tag deployments over 10 years on a number of the different species of baleen whales that exist to try and get an understanding of, as you go from big to small in baleen whales, how much these whales eat. And this to me is one of the cooler images that we've been able to put together. These are drone images of all the different whale species that we work with. And these are all to scale. And it's really fun to look at these animals all side by side and just see how their body plans are different and how they're morphologically adapted very differently. So we have, obviously, the biggest of the big is the blue whale. You can see how narrow and thin they are. Fin whales, the next largest whale. Humpback whales, we kind of call them the minivans of the sea. They're not designed for speed or really anything in particular, but they're a really good catch-all for doing everything, and they can haul a lot of luggage. And then at the very end, we have Antarctic minke whales, which are the smallest of the baleen whales. So you can look at these animals and just see how similar or different their body plans are, and that really impacts the behavior of these animals. So in order to study them underwater, we've worked with engineers to build these biologging tags that we put on the backs of animals, stay on for about a day at a time, and measure continuously the motion of the animal in three-dimensional space. So it has accelerometers, just like your smartphone or almost any device you have today, that tells you about the orientation sort of in X, Y, and Z dimensions, magnetometers and other sensors that just allow us a little bit more precision to reconstruct the three-dimensional movement of these animals. The tags have these other computers on board that help us record audio and video. So we're hearing the sounds the animals make, as well as all the ambient noise the animals are hearing. And then the video is really compelling for us because it helps to contextualize why an animal is doing certain behaviors. And I'll show you some cool clips about that. This is clearly the most fun part of the work, getting out on small boats, being up close to these animals, which are absolutely amazing, putting these tags on and then letting the animals kind of go about, do their thing. The tags have to store all the data on them, so when the tag falls off, it floats at the surface. This little tail sticks up, and it's a VHF transmitter that we can listen for with a radio receiver and antenna. We go pick up the tag, download the data, recharge the battery, and can slap it on a whale sort of the following day. So these are really remarkable tools that we've developed over the last 15 or 20 years. All right, here's sort of the business end. Of course, I'm only going to show you videos where it works and the conditions are beautiful, right? We never miss, nothing ever goes wrong. The tag sits at the end of this about 20-foot carbon fiber pole. The whale volunteers to come up close enough that we can just slap it on its back, and the whale goes about its business. And one of the things when we develop these tags is it's really important that the animals are not impacted by this tag. The animals go about their business. They basically are back to what they were doing before we tagged them almost immediately. And the tag size relative to the animal doesn't impact their behavior at all. And that's something you need to be considerate of if you put a big backpack on a penguin, for example, or you put a big tag on a small animal. It may affect what that animal is otherwise going to do. Once the tags are on the animal goes about and becomes a cinematographer for us. So you're on the back of a humpback whale. That's part of this massive feeding aggregation. This is off the coast of South Africa. So from the whale's perspective, you can see other animals. That gives us a really great insight into how these whales feed and do their activities. You can see the prey. You can see some other animals in the frame as well. This is a really cool video. This is on the back of a humpback whale here in Monterey Bay. If you think the planetarium's cool, this kind of looks like going through an asteroid field of stinging sea nettles. But again, the video helps us contextualize why animals are doing certain things. And you're going to start to see a whole bunch of sea lions, literally hundreds of them, that are feeding in concert with these whales. And if we didn't have this perspective of what was happening around the animal, we may be spurious and make conclusions about why an animal does certain things in one situation versus another without knowing what the context is. Maybe these sea lions are kind of ticking it off and the animal will make some sounds or do something differently than it would if those sea lions weren't there. Sort of another way that we can start to understand the environment or the context for these animals is to look at the physical environment. So you're on the back of an Antarctic minke whale here underneath sea ice. You can see the sea ice all up here at the surface. These are just the CSI sensor values that make us look really smart, so they change and they have lots of color. But what you're looking at here is the blue line here is the depth of the animal. Oops. The blue line is the depth of the animal. The green line and the purple line are indications of when the animal is speeding up and doing a lot of motion. So what this tag can tell us because of this video is how frequently does the whale feed under sea ice versus open water? How much time does it spend in different behavioral states in different sort of parts of its environment? This is critical when we want to study something like climate change. How important is sea ice to this species? And if it goes away, what behaviors is it going to affect? You're going to see the minke whale feed very quickly here. The tag is on sort of the left side of the back. The animal is now diving. You'll see it speed up very quickly and open its mouth right there. And you can see all the prey that is sort of passing by it. So we can use this tag data to corroborate our video and say, okay, now we know different sensor values tell us about when these animals feed. We can then go back to the data where we don't have video and say, where do we see these similar kinds of peaks in some of these sensors that may indicate when a whale is feeding. Another thing we can do is try and put the movement of that animal into three-dimensional space. So instead of just thinking that the animal goes up and down, we know that these animals actually use, media not found, my bad. Basically what we can do is we can turn the motion of the animal into like a roller coaster ride. And what you would see here is the animal, this ribbon really just represents the orientation of the whale. And over here you can see that the animal is doing a lot of maneuvering around in the environment. This is something you can't get just from 2 dimensions of data. This tells you a whole lot more about how much space the animals are actually using in the water column. And this becomes really important when we study individual feeding behavior. Has anybody here ever heard of something called bubble net feeding? Few people? Okay. So humpback whales have this really remarkable strategy where they create a ring of bubbles around a prey patch, and they make these sort of spiraling loops of bubble to help contract the water around prey, consolidate the prey, and then they come up underneath and feed through it. It's this really cool way of using tools to make foraging more efficient. And what each of these shows you is a different foraging strategy by an individual humpback whale. Kind of like, think about a golf swing or a baseball swing. They all have very slight differences in how they do it, but when they're hitting the ball, they're doing the exact same thing. So for example, this animal here comes in from the bottom and it makes sort of 1.5 loops and then comes up. This animal here does 3.5 loops before coming to the surface. This one here does 2 loops before it comes up. Got a little problem here. This guy's not really figured things out, but this is really interesting. This is a juvenile animal. That behavior hasn't kind of crystallized, so it's just kind of figuring out what to do. Probably a little hungry still, but it shows us that there is individuality among these whales and that they have differences and they have nuances that individuals do, which is really remarkable. On the right here, this just shows this graph right here. The black lines are right-sided. This other line is left-sided. When we look at how whales perform behaviors, if they're making bubbles in one particular direction versus another, or they roll when they feed one direction or another, we find excuse me, the same proportion of right-sided to left-sided whales as we do handedness in humans. So for any lateralized behavior in these animals, they all in the vertebrate kingdom follow this 85 to 90% are right side dominant, 7 or 8 are left side dominant, and some animals are ambidextrous. And this is great. This aligns exactly with what we know about how the vertebrate brain is evolved and how the left hemisphere of the brain connects contralaterally to the right side of your eye. The motor functions of repeated behaviors tend to be right side dominant in all vertebrates, and we see this demonstrated in whales as well, which is a pretty cool thing. Okay, so now that we figured out we can understand how many times a whale feeds, we're really good at saying, yes, this is when the whale fed. The next thing that we want to do is understand how they're interacting with their prey. Excuse me. So what we do is when we have a tag on an animal, we have these echo sounders that I mentioned before that hang off the bottom of the boat that are sending a sound signal into the water. It's bouncing off of things in the water that scatter sound, and the amount of return that comes back tells us about how hard or how much stuff is in the way. So down here, this black line here is the bottom of the ocean. The areas that are highlighted as hotter colors are higher densities of prey. The blues and greens are less dense prey. Does that make sense? So now what we want to do is we want to say, where was the whale in the water column when it was feeding, and what was the density of prey like where that animal was? Okay. So now we can understand how changes in prey affect when and where whales are feeding in the water column. So we'll go to this graph now. This is what we call a heat map here. So this is showing from the surface of the water down to deep water and going across a 24-hour period from dawn to the middle of the day to nighttime. And the colors here tell us about how intense whale feeding occurs at a given depth and a given time. So what you see here is that during the daytime, there's no feeding near the surface. There's a little bit in deep water, and then there's this transition as you go from day to night, and then the whales go absolutely bonkers near the surface once it's dark out. Okay? Now, why are they doing that? This is what the prey look like during the day. Okay? So this red line here is the bottom of the ocean. These little blobs that are kind of green and yellow are the prey patches. None of them are up at the surface. They're all at depth. And relative to what you saw before, they're relatively sparse. There's none of those really hot red patches. So during the day, the whales are feeding a little bit down deep, but they're not spending a lot of energy doing it. At nighttime, the prey do something very different. The prey are now up at the surface, and you can see these patches have consolidated. They're much more red, much more packed with density. The whales are basically modulating their behavior and taking advantage of the prey when they come to the surface and become more dense. So it's more efficient for the whales to feed. So rather than go out foraging for celery, they're waiting for DoorDash to bring them a burrito at night, right? It makes perfect sense. And you don't get big in the ocean by not being smart or being efficient. And this is how the whales have figured out how to be efficient. They're taking advantage of how the prey have evolved to move up and down in the water column relative to day and night. The prey aren't responding to the whales are responding to the prey and taking advantage of them. Okay, so Now that we know the prey density that the whales are targeting, how many times they're feeding in a given day, we can start to make estimates and really informed empirical estimates about how much the whales eat. Not only how much they eat, but then what's the consequence of what they eat, sort of on the back end of things. This was a paper we published in Nature a couple years ago, and the take-home message, which I'll kind of give away right now, is that whales eat a lot more than we thought. If we just estimated how much a whale ate based on metabolic rate equations, Kleiber equations, the animals would feed a lot less than they actually do. And because they eat a lot more than we think they did, they actually are recycling a lot more nutrients into the water column than we thought that they possibly could be, which means that they are actually helping to promote and stimulate primary production in the places where whales are and where they're foraging. There's a little, I know there's some kids in the audience, so I won't go all the way with the analogy, but the you don't blank where you eat is actually wrong for whales. You want to do that because you actually help to stimulate growth in those places. So hopefully you recognize what I was saying. Okay, so in order to understand how big a whale's mouth is, we went back to the 1920s to when 2 million whales were killed in the Antarctic, and fortunately the zoologists did a lot of measurements showing us how big the mouths were on these whales. So this is a blue whale that's up on a platform. The mouth of the whale extends from right here at the tip of its jaw, basically all the way down to its umbilicus. Those patterns or those striations that you see are very extensible throat groove blubber that inflate when the animal opens its mouth and allows them to take in a huge volume of water. So we estimated that, let's say you're a 12-meter long whale, that's about a 35-foot long whale. Every time you open up your mouth, you can get 75% of your body weight in water in your mouth at once. So if this is a 10-ton whale, you can get 7.5 tons of water in your mouth at once. And if you do that in a place where there's a lot of food, the opportunity to get a lot of food is pretty good. Well, the more remarkable thing is that this scales with body size. It scales volumetrically. So by the time you are a blue whale that's maybe 75 feet long, you can get 133% of your body weight in your mouth at once, right? So imagine you're a 100-pound person. Imagine fitting 133 pounds in your mouth. Not possible given our anatomy, but this really shows you the bigger you are, the more efficient you can be. The more efficient you can be, the more you can eat. The more you can eat, the bigger you can get. It's this very nice kind of circular positive feedback loop that allows big animals to get really big, which is really absolutely amazing. If we just wanted to graph out then the engulfment capacity, how big the whales' mouths are, you obviously see going from minke whales up to blue whales, there's this nice trend of increased engulfment capacity. If we then multiply that by how many times in a day a whale feeds, we see some really cool things. So these are blue and fin whales here, and you see the number of times that they could feed is about 200 times in a day. That is limited mostly by processing and handling. It takes a blue whale about a minute to accelerate, open its mouth, close its mouth, and push out all that water before it can feed again. So the feeding rates of a blue whale are very limited. The smaller you are, like a humpback whale, the more times you can feed in a given day. But, because your mouth is so much smaller in a humpback whale, you can't process nearly as much water. So even though a blue whale feeds maybe half as much as a humpback whale, it actually filters about 15 times more water in a given day because of the size of its mouth. So then when we multiply that by how much prey we measure in the vicinity right where whales are when they're feeding, that gives us the ability to then say how much food is a whale eating in a day. So blue whales up here, fin whales, humpback whales, this is in the Pacific, and then humpback whales, minke whales in the Antarctic. This doesn't scale in a really great, it's not log scale, but basically blue whales are eating about 12 to 14 tons of food a day. Huge amount. Even humpback whales eating about 4 to 5 tons of food on a given day. If we look back in the literature, before we had empirical data where we measured this, the estimates just on basal metabolic rate suggest that blue whales probably eat about 2 or 3 tons a day, fin whales maybe 2 tons, and humpbacks only 1 ton. So grossly underestimating the amount of food that these whales eat, which means that we really need to reconsider what a healthy ecosystem is that can support all of these animals. Another thing that's really interesting is to look and see how feeding changes throughout the year for an animal. So the life history of a baleen whale, you go to a feeding ground, you end up there early springtime, late springtime, you spend about 4 or 5 months there feeding intensively, then you migrate to a breeding ground. You don't eat along your migratory route, you don't eat while you're breeding, you migrate back, you spend about 8 months of the year not feeding. So 4 months of the year you are intensively feeding, and you need to gain all of the energy you can for 1 year in a very short period of time. And all this graph shows us is how the feeding behavior of a whale changes throughout the season, from the beginning of the season to the middle of the season to late in the season. And one of the really interesting things that we see in a place like the Antarctic, when they arrive in December or January, they're feeding 24 hours a day. The prey are up at the top of the water column, there's continual sunlight and productivity. The whales feed almost continuously. As you get later and later in the year, once you have nighttime that occurs, those prey do that vertical migration that I showed you before. The whales stop eating for about half the day and only feed about half as frequently towards the end of the season as they do at the beginning of the season. So their feeding rates change dramatically from the beginning to the end of the season. Interestingly though, if we look at the body size of whales from drones, this is what a humpback whale mom and calf look like when they arrive on the feeding, on the feeding grounds. Relatively skinny, not skinny. This is a really healthy calf, right? The end of a feeding season, mom is full, the baby is full. They gain energy in a linear way. So even though their feeding rates decrease, they keep putting on energy at the same rate. And so what that tells us is that the prey are actually becoming more aggregated or denser or higher quality later in the season. So there's no period in there when it's not critical for the whales to be feeding. They're constantly putting on weight. That whole period is really critical for them. And if we start thinking about conservation and management or overlap with fisheries, we now have evidence to suggest that these whales really need food all the time. There isn't a period that's not critical for them. And I'll get to that in a little bit. But now once we understand kind of what whales do to take in and consume, trying to understand the effects of whales and what they have on their ecosystem is the next question. For a long time, we thought about whales as sort of the end of the line for a food chain, but obviously the recycling of nutrients is really important. And we started to consider baleen whales as ecosystem engineers, much like a beaver here. An ecosystem engineer is a species or animal that modifies, maintains, or creates habitat by either directly or indirectly modulating the availability of resources to other species. And this is how whales provide resources for other species, is through iron fertilization. So this is a hypothesis that's been called the whale pump, and effectively what the thought is here is that whales go down in the water column, they are grabbing and eating a lot of food, bringing it back up to the surface, and then those nutrients that you see coming out of the whale, this is a tag that happened to find its way to an unfortunate position for the tag, great position for us, but it allowed us to really understand and recognize that the animals are recycling a huge amount of nutrients. We, not me, other chemists, I don't understand chemistry at all, chemists have looked at the constitution of the feces of these animals, and there's a huge amount of iron that is in there. And when we look at surface waters in many ocean ecosystems, one of the most limiting nutrients for phytoplankton growth is iron. So these animals are bringing up iron to the surface, replacing it up near the surface, and when this occurs during summer, when there's sunlight and other great opportunities for growth, the whales are seeding, recycling nutrients, promoting and stimulating growth in the environments where they are. Now, today is very different from 100 years ago, and this is one of the main issues that we have. So what this graph shows us is, this is basically the feeding season for a whale for 4 different species. And we've said if a whale feeds for 2 months or 3 months or 4 months, how much iron is it recycling? And the reason that there are 2 lines here is because This is what whales used to do before we killed them, and this is what whales are doing today. So blue whales are sort of the best example we have. We killed 360,000 blue whales in the Southern Ocean in the 20th century. If you multiply that number by the feeding days that an animal did, this basically shows us how much iron blue whales would have recycled. Let's call it 5,000 tons per year of iron that whales were putting back into the ecosystem. Today, it's a flat line because there's basically no more blue whales. So there's very little stimulation of growth outside of just the regular oceanographic processes that whales aren't contributing to. And you can see for all the species that we've killed off, there are huge differences now in iron production in the ocean and recycling of nutrients. Some of the things that we see in terms of how much prey is available to these animals, we think is a direct impact of whales not being abundant or part of those ecosystems anymore. And that's sad. However, there are some bright spots, and there's some things that we need to consider in terms of conservation success stories, but still red flags. So in the Southern Ocean, we killed all the whales, boo-hoo, it sucked. However, you give whales a chance, you leave them alone, there was this huge amount of prey that wasn't being consumed by whales called, excuse me, the krill surplus hypothesis. You take out all the things that are feeding on krill, there's a huge amount of food that nothing is eating. The animals that can take advantage of it and eat it the most quickly are going to benefit. Humpback whales grow quickly. They have a central breeding ground, which means it's easy to find a mate. And humpback whale populations have increased quite significantly in the Antarctic. We measure pregnancy rate in these whales with little biopsy samples that can allow us to measure reproductive hormones. And we found that about 2/3 of the females in any given year are pregnant. There's so much food, we thought that about 1 in 8 females can be both lactating and pregnant at the same time. These animals have about a 12-month gestation period. So imagine being a pregnant mom, having a calf that you're weaning, and having enough food available to you, let alone the obvious issues with having to handle and be present for care of an animal, but just the energy that's available to you is so high that you can maintain a calf and grow one inside you. Now, what we've been able to do over the last 10 or 12 years is measure the annual pregnancy rates, and this is what this green line shows in humpback whales in the Antarctic, and you see that there's a lot of variation. There's some great years, then there's some down years. What we've been able to do is link the amount of reproductive success in these whales to the environmental conditions. And in the Antarctic, that means how much sea ice is present. And how much sea ice is present has a direct effect on how much krill survive their first year to be available for fur animals the next year. So the fact that we can show in a bad ice year, the reproductive rates of whales decrease means that prey is not unlimited. Prey is actually limiting to the point that not as many females can get pregnant in a bad ice year. And this is a red flag because, again, we thought that prey were unlimited. There was this huge surplus of food. And if in the Antarctic, whales can be limited without blue whales or fin whales or many of the other species coming back to their pre-exploitation levels, it means that the system is changing, can't support nearly as much food as it has in the past, or whales as it has in the past. This recognition sort of pushed me and pushed some of our colleagues in conservation to start thinking about how do we come up with new strategies to protect whales, their ecosystems, and the places that are important for whales. And in the past, we typically thought about where a whale feeds, that's important. Where a whale breeds, that's important. And then there's just these migratory corridors where the animals go in between. But we're recognizing more and more that these corridors that the animals use are critical habitat. Basically, anywhere a whale is, it's critical to conserve and protect. So we came up with this really sort of ambitious effort to try and aggregate all the data that researchers had published on the migratory pathways and corridors of whales around the world, and tried to put that onto a map and better understand the threats that whales are facing throughout all of their ranges, not just where they feed or where they breed. And this is a really kind of cool image. The different colors represent different species, but it shows you the tracks of all of the baleen whales that we've tagged as a community over the last 20 or 30 years. And you can see that there are these vast areas of the ocean that are really critical corridors that are really important for these animals that we need to think about. Now, These represent a lot of animals that we've tagged. It doesn't represent the animals that we haven't tagged. So don't think of this as a comprehensive map showing that because there's nothing here, there's no whales here. No, we just haven't tagged anything there. But we have a lot of information to show us where some of these really important corridors are, like along the US West Coast for blue whales, for example. The next thing to do is to overlay or start to understand where human activities are influencing these animals the most. So climate change in the Antarctic on their feeding grounds is one thing, but we have things like shipping and fisheries that occur almost ubiquitously around the world, and overlaying maps on where those things are the most sort of prodigious or where shipping lanes tend to occur is really valuable for us to overlap with where whales are so we can better understand the risks that these animals face sort of throughout their life cycles. In the Antarctic, this is sort of an Antarctic view, and you can see we've tagged a whole lot of whales, and there's some very important areas for them. One thing that we are starting to look very closely at is the association between a krill fishery and where whales feed. I've mentioned that prey is already limiting to these animals, and there are commercial fisheries that go out and harvest the krill at the same time that the whales are feeding. Obviously, this puts them into direct competition with one another. The more we understand about the needs of the whales, the more we can hopefully work with industry to set better standards and have as minimal an impact on these whales as we possibly can. Unfortunately, competition for the prey isn't the only thing that happens with fisheries. Whales end up in nets too, despite our best efforts. So understanding sort of the scope and scale of these overlaps is really, really important. Excuse me. I apologize. Now, one thing that we as a community have not done well is to develop marine protected areas relative to the places that are important to the animals. Right now, marine protected areas are more about us modulating what we do in blocking off areas of the ocean for our own use. We did a study a couple of years ago where we took 4,000 tags that were put on 17 different species of animals, and we let those animals tell us where the ecologically important areas were for them. So it's pretty obvious if you look at this map, the areas where you have high densities of tracks are the areas that are really important for those animals. When we overlay where we have developed marine protected areas for those species, what we find is that currently these marine protected areas only cover about 27% of the areas that are important for the animals. About 75% of them are just in areas that have no real value for the animals. So what's the point of having them there? And even if we look into the future of things that have been proposed, we only get a little bit of a modest increase. So using the animal's perspective to tell us about where it's important to protect them is critical as we move forward for conservation purposes, because we need to give the animals the greatest chance at success. We need to do it in the places that are the most important for them, not that we think are the most important for us. So as you move forward, I think it's a really important thing to think about how we start planning conservation strategies. Sorry, this is a little bit overlapping on itself, but what I wanted to sort of share from this was the power that a single report can have. We wrote this report about 1.5 years ago. It got promoted very well through WWF. There were over 270 media stories about it globally. It had a reach of 730 million people, 19 million people on social media. This to me is sort of direct evidence that working not just in the scientific community, but with organizations and groups that have a huge capacity to reach a lot of people, you can get information to people very quickly, hopefully in a compelling way, and in a way that people can digest, and again, utilize to help better protect and manage our marine resources. So hopefully that was a little bit of an introduction to how we study these animals, why we study them, and why I think it's important for these animals to persist, not just for our own needs, but for the ocean in general and health of the ocean. So I really appreciate you guys sticking around. Again, I would really encourage and invite anybody from here to come down to Santa Cruz, go out whale watching, come visit us at the Marine Lab, or do whatever you want. Come down for a surf. So thank you. I'd be happy to answer any questions.